Hi guys, Gibson here. Today I'm going to walk you through a lesson on resonance in air columns. Now, hopefully you had a chance to watch the previous video by Dr. Lewin where he talked about resonance, the concepts of that, and all the different examples, particularly in musical instruments. So he looked at resonance on a string, resonance in a air column or air tube, and that's the piece that we're going to take a deeper look at today. So here are our two objectives. First, be able to describe how a standing wave forms. Now, he alluded to a standing wave in the video, but didn't formally define it. So we're going to do that here. It's a very important concept in terms of resonance. And then we'll be able to apply that to two cases, columns that are open at both ends or closed at one end, and how are their resonance set up, and how can we solve for things like wavelength, the length of the tube, the frequency, speed of sound, any of those parameters uh, we can solve for resonance and air column type problems. So let's just do a little bit of review. We've already talked about this. Natural or resonant frequency is the frequency at which an elastic object, once energized, will vibrate. So all objects have their own natural resonant frequency that they like to vibrate at. Um, at that resonant frequency, it just requires a minimum of energy as an input to keep it vibrating at that frequency. And the actual resonant frequency depends on a lot of things, but primarily the object's shape, its elasticity, what it's made of, the density of the material, et cetera. All those things combine to produce a natural or resonant frequency. So the classic example here is our tuning fork. Depending on the size, the thickness, the length of the forks, that all determines what its natural resonant frequency will be. But each tuning fork has a unique frequency that it vibrates at. Resonance itself is when the frequency of a forced vibration of an object matches the natural frequency or resonant frequency of the object. And the result is that we get a very dramatic increase in the amplitude that that object is going to vibrate at. So the two examples we looked at in the previous video was resonance of a wine glass. And you can see by this video here in slow motion, if we apply a frequency that matches that of the wine glass, it begins to vibrate. And at some point, the amplitudes will be so great that the glass can no longer withstand that, and we see it shattering here. Here's another example, kind of a cool video that was taken from inside a guitar, but you can see the 6 guitar strings in slow motion as it's being played, and you can see the actual resonant frequency as it travels along the guitar string. And you can notice the thicker guitar strings have longer wavelengths than the thinner guitar strings. The thinner guitar strings will produce a higher frequency at a shorter wavelength. So resonance can occur in all objects. Resonance in a string is a classic example. The one we're going to look at today is resonance in a air column. So before we jump into that, let's define this concept of a standing wave. Now, standing waves is a wave that appears to be standing still. That's where the name comes from. And it's produced by the interference of two waves moving in the opposite direction, okay? So let's put a little animation up here that shows that. So here's our blue wave moving to the right, the red wave moving to the left. And as they interfere with each other, the black wave below gives us our interference pattern. So notice what happens. We get a wave that appears to be standing still. In other words, the nodes and antinodes remain in one location, and we just see the amplitude change at the antinodes from a maximum to a minimum. So I'll just let this run another second here. You can watch this. So here's how a standing wave is formed. Two basically identical waves traveling in opposite directions, and then how do they interfere? Okay, so let's think about how would we produce two waves that are identical but traveling in opposite directions. So before we jump to that, let's just quickly define, right, what we mean by the parts of a standing wave. The node, the antinode. The nodes are the part that remains stationary, or we would say have zero amplitude. The antinodes are the part where the largest amplitude occurs. So in the simplest form, right, we would have one antinode in the center and then two nodes at the end. If this was a vibrating string, it'd be where we're holding the ends of the string. Those would be the nodes. So we can get different combinations here. As I just mentioned in the previous example, the most simple case is where the standing wave represents half of a wavelength. So we'd have two nodes and one antinode. But we can get other harmonics. This case, right, we would have twice the frequency, so we get now a full wavelength, three nodes, and two antinodes. And then the last case we could have, if we tripled the frequency, we would now have 1.5 wavelengths. We would have four nodes and three antinodes. Okay, so depending on the frequency that we're exciting in this case, a vibrating string with, we can produce different numbers of nodes and antinodes. What we're basically producing is different harmonics of the resonant frequency. So back to this question, how do we produce a standing wave in a resonant tube? Well, let's go back and talk about two cases for how the end of a string, in this case, is anchored. And if you remember from our Slinky labs, we tried to observe this, right? We did one case where we had a hard anchor, and we noticed that the wave comes back on the opposite side from an amplitude standpoint. If we have a soft anchor, it comes back on the same side. But the key difference here is that with a hard anchor, the end of the string is not allowed to move. That's going to produce a node, right? A point where the amplitude remains zero. For a soft anchor, we get a antinode because we can allow that end of the string to move up and down with the amplitude as the wave comes in and reflects. So if we apply this to an air column, we can think of the open end of the tube as a soft anchor. In other words, that's where we will have a antinode. The hard or the closed end of the tube will produce a hard anchor. So that is where we're going to have a node. So if we were to draw in a wave or a little animation here of what it might look like in the tube, we would have a antinode at the opened end and a node at the closed end. Okay, so let's label that here. We can ask the same question, what would happen for a tube that is open at both ends? Well, we're going to get antinodes at both ends since both of those will be treated as a soft anchor. So the amplitude will be allowed to move to its maximum positive and negative at each end of the tube, and we'll get a node in the center. Okay? So it's this reflection of the wave from either a open or closed end that produces a wave that travels back the opposite direction. So this is what allows a standing wave to be created. It's that reflected wave coming back from the end of the tube in this case and interfering with the original wave coming down the tube. And that's what produces this standing wave or resonance in a tube. And we'll have these two cases that we'll continue to look at here, closed at one end or open at both ends. So let's go a little deeper into this case of a tube that is closed at one end. Let's say we excite that with a tuning fork, right? Because we do need to have some energy source for the sound. So that sound wave will travel down to the bottom of the tube. Now, since this is a closed tube, right, it's going to be treated as a hard anchor and reflect back up to the open end of the tube. And that reflected wave will interfere with the wave traveling down and produce our standing wave. So if we were to draw in what the amplitude of that wave might look like, What we're really talking here, since it's a sine wave, is that we get maximum variation in pressure of the air at the open end, and we get minimum variation in pressure at the closed end, or basically a node. So let's label those. We have our area of high pressure at the open end, and we have an area of low pressure or zero pressure variation at the closed end. So the question is, what fraction of a wavelength does this tube represent when it resonates at its fundamental frequency? Well, if we look at how much of a wave we've drawn inside the tube here, we see that it forms a quarter of a wave. So let's go back to our model, right, of a vibrating string. We basically have one node and one antinode, so that makes up a quarter of a wavelength. So let me get my highlighter going here to highlight some of this for you. So right here is the key. That if we have resonance in an air column that is closed at one end, that first harmonic will form at a quarter of a wavelength. So whatever the length of the tube is, that will represent 1/4 of the wavelength for that particular frequency. Let's go through the same exercise now, but for a open tube. So open at both ends, which means we have a soft anchor at both ends. Again, we'll provide some energy here with our tuning fork. The wave will travel down, reflect off the bottom, and we get interference that produces our standing wave. So in this case, right, because we have a open or soft anchor at both ends, that will give us antinodes, areas where the air pressure will vary greatly from positive to negative. And in the center, we will get a node, a low pressure area, or an area where the pressure does not vary much. So same question, what fraction of a wavelength does this tube represent? Well, let's go back to our model of a vibrating string here. In our tube, we have two antinodes and one node. So what portion of a wavelength is that? Well, here's how we would draw that, right? From one antinode to the next, including a node, that would give us a half of a wavelength. So that's the other key concept here, is that if we have a tube that is open at both ends, the fundamental resonant frequency will occur at half of the wavelength. In other words, the length of the tube will represent 1/2 the wavelength of the sound wave. Okay, so let's look at a couple other cases here and understand how the harmonics would form. So we'll go back to our first case of a closed tube, right? The first resonance, we already agreed, occurs at 1/4 of a wavelength. Now, where would the second resonance or second harmonic occur? Well, if we increase the frequency, right, we would then get a second resonance. And if you look at this wave here, we have a half a wave plus another quarter. So we have 3/4 of a wave at the second resonance or second harmonic. If we increase the frequency further, now we can look at the standing wave in the tube and decide what portion of a wavelength does this represent. Well, I can see a full wavelength, right, from here to here, plus another quarter of a wavelength. So we would get basically 1 1/4 or 5/4 of a wavelength. So what do we notice as we continue to increase the frequency to the other harmonics? Notice that the number of wavelengths in the tube continues to increase by half a wavelength each time. So let me get my pointer here. So at the first harmonic, we had 1/4 of a wavelength. At the second harmonic, we had 3/4. At the third harmonic, we have 5/4 or 5/4. So notice each time we're adding a half of a wavelength more as we increase the frequency. What if we went up to the fourth harmonic? Well, that would give us another half or 2/4. That would get us to 7/4. And at the fifth harmonic, that would be 9/4, okay? And it'll just keep increasing that way. So let's now look at the case where we have an open at both ends and see as we increase the frequency to the other harmonics, right, which wavelengths will we have? So we already talked about in the previous slide that the first resonance would occur at half a wavelength. If we increase the frequency, basically double the frequency, now we see that we have a full wavelength here, right? We've got 3 antinodes and 2 nodes, which makes up a full wavelength. And then if we continue to increase the frequency or triple it, we now will have a 1.5 wavelengths. So with an open tube, we're still increasing the number of wavelengths by 1/2 with each harmonic, but we start at 1/2 of a wavelength. In the closed tube, right, if you remember, we started at 1/4 of the wavelength. Okay, so this may sound kind of confusing, but as we work through some example problems here, you'll kind of start to see how this works. Most of the problems we're going to look at will all just deal with the first harmonic or resonance and not worry too much about the higher harmonics. So in summary, if the column is closed at one end, our first resonant or fundamental frequency forms at 1/4 of the wavelength of the frequency. And we'll see this a little more as we get into some example problems. It's only the odd harmonics that will form. So in other words, the first, the third, the fifth harmonic. If the column is open at both ends, the first resonance will occur at 1/2 of the wavelength of that sound wave, and all the harmonics will form. So we'll get the first and second and third and fourth harmonics, okay? Now, there's a set of equations that we can use. Some of these we've already been working with. Let me move hopefully that video out of the way. And these are for the 2 cases. Now, if you remember Professor Lewin's lesson and some of the problems that I gave you guys, we had this one equation. Let me go back to my highlighter here, that he gave us for finding the frequency in a resonant tube. Okay. So n is equal to the harmonic number. So if it's the first harmonic, basically it's the speed of sound divided by twice the length of the tube. Okay, so we've already had some experience using that formula. Now, if you look at that same formula applied to a closed-in tube, it's slightly different, except now instead of dividing by 2, we're going to divide by 4. Now, why is that? So remember, a closed-in tube, the first resonance occurs at 1/4 of the wavelength. Okay, so that's why we're dividing by 4 here. The opened-in tube, the first resonance occurs at 1/2, so that's why we're dividing by 2. Okay, so that's the reason why we see that one difference, but otherwise the formulas work the same way. So we can take this formula, knowing the relationship between frequency, go back to my pointer here, between frequency, velocity, and the wavelength. So we could rewrite the equation solving for the wavelength. 4 times the length of the tube divided by which harmonic, or for the open tube, 2 times the length of the tube divided by the harmonic. And then we could rearrange this again if we want to know the length of the tube and we know the wavelength of the standing wave, we could also calculate that. And then down below is a summary again that we only get the odd harmonics for a closed-in tube and we get all harmonics for an open-in tube. Okay, let's look at a couple example problems here. I'll put this down here for now. So we have resonance in an air column with a closed end. The length of the tube is 0.174 meters, and the tuning fork frequency is 480 hertz. So assuming the first resonance of forms, we want to find the speed of the sound in the tube. Okay, so let's put our tuning fork up here at 480 hertz, right? Creates a sound wave that goes down and reflects and sets up our standing wave. Now we can use the wave equation here. I'm going to change over to, whoops. Sorry about that. Hang on, let's go back. I just want to go to my pen here so I can write a little bit on this. We're going to use our wave equation, right? Velocity equals the wavelength times the frequency. So what we're after is the speed of sound, right? We're trying to solve for V. So what can we fill in here? Do we know the wavelength of the sound? Because if we know the wavelength, we already know the frequency up above, right? That's 480 hertz. So we could then solve for the velocity. But first we have to find the wavelength. Well, we know that with one end closed, we're going to have 1/4 of a wavelength inside the tube. So since we know what the length of the tube is, 0.174 meters, and we know that has to be equal to 1/4 of the wavelength, we can find the wavelength by simply multiplying by 4, right? If this tube represents 1/4 of the wavelength, the full wavelength would be 4 times that amount. So here we get our wavelength, 0.696 meters. So now we can take that, right, and plug it into our formula up here. Try and draw an arrow. Our frequency we know, right, is 480, so we can plug that in. And if we do that, we now get our velocity, which is 334 meters per second. So if you had a tuning fork and you knew the frequency, and you could adjust the length of a tube to get it to resonate, you could actually use the measurements of that to determine the speed of sound. Now, if we were together in class, I'd actually have a little lab for you guys that you would do exactly that. But we'll have to settle for these types of problems for now. All right, let's look at one more example here. Resonance is created in an air column that is open at both ends. The speed of sound is 340 meters per second. If the fundamental or first harmonic resonant frequency is 425 hertz, what is the length of the tube? Okay, now this is open at both ends. So again, we'll put our tuning fork up here, 425 hertz. It travels down and reflects and creates our standing wave. Now remember, with a open at both ends, we're going to get a standing wave that is a half a wavelength. Right? It has antinodes at each end and then one node in the center. So let's put that up here. The length of the tube represents half of a wavelength. So we want to know what that length of the tube is. So again, if we go back to our wave equation, if we can find the full wavelength, then we can simply take half of that to be able to find the length, right? Because that's what we're trying to do. What is the length of the tube? Okay, so we know the frequency is 425 hertz. We know the speed of sound is 340 meters per second. So we can find the wavelength by just plugging it in here, right? Frequency divided by velocity. I'm sorry, velocity divided by frequency, and we get 0.8 meters for our wavelength. So the wavelength of a frequency or sound wave of 425 hertz would be 0.8 meters. So if a full wavelength is 8 meters or 0.8 meters, then half of a wavelength, right, would just be simply half of that. So let's just take half of that 0.8 and we get 0.4. So the length of our resonant tube would be 0.4 meters. Okay, so a couple examples there, one with a closed-in tube, one with an open tube. The key thing when you begin to solve these problems is make sure you establish if I have a quarter tube, or I'm sorry, a closed-in tube, it's going to represent a quarter wavelength. If I have an open tube, it's going to represent half a wavelength. Okay, so let's wrap this up. We've described how standing wave forms, basically two identical waves that are interfering, And we can create that by sending a wave down in one direction and having it reflected back. And then those two waves will interfere and form a standing wave. And now we've looked at a couple problems, types of problems that we can solve for resonant tubes or air columns that are either open at both ends or closed at one end. Okay, so once you finish watching this video, there'll be a Google form worksheet that you can work on that'll give you some practice with these concepts and solving a few problems. All right, thanks.